Swayam Prabha. Digital India. Educated India.
So, in my previous lecture, I have discussed about various ground improvement techniques to mitigate the seismic or liquefaction hazard, and then we discuss about the stone column, and we discussed there are different effects like reinforcement effect, then the densification effect or smear effect, then the drainage effect. In the drainage effect, because there is a permeability of stone column is more than the permeability of the surrounding soil, and another one important effect is the clogging effect. So, we will discuss how we can incorporate all this effect in our design to mitigate the liquefaction hazard. So, now we are talking about that when you design it or analyze this system, we consider one approach that is called unit cell approach. So, what is this unit cell approach? The unit cell approach, as I mentioned, that column can be these stone columns are installed in grids. So, this can be a triangular grid, this can be a square grid. Suppose if this is a square grid, it can be a hexagonal grid also, but the most common grid patterns are triangular and the rectangular. So, we will discuss in this class the triangular or the rectangular grid pattern. So, if it is this is our rectangular grid and this is a triangular grid. Okay, again so this is a rectangular grid pattern. Okay, this one is a triangular grid pattern. So, now when you are talking about the unit cell, so among these all columns, suppose these are the stone columns, we will consider say one particular column and we will assume that the behavior of all the columns are same. So, that assumption is most of the cases it is valid except for edges or the surrounding the edge of any structure, except that these assumptions is valid. Okay, so that's why still we are using this unit cell approach. So, now suppose here we consider the area surrounding this column. Suppose this is our column, so this is the area. So, we are assuming that this blue area is the area will be influenced by this stone column. So, similarly all the areas they will be influenced by these individual column. So, now we will consider similarly for your this particular triangular grid. So, for the particular this triangular grid, we are assuming this hexagonal area will be influenced by this column. So, this is for triangular grid, this is for square grid. So, now this grid, if I take now this column, this is the column and for square grid its surrounding influence area. Now we are taking this column and surrounding influence area. So in case of square grid, the influence area is also square, but in case of triangular grid, the influence area for a particular column is your hexagonal in nature. So you can see that it can be actually like this. Okay. Like this. So this every column has its own influence zone, and for the square grid it is the influence zone for every column, and these are same. Okay, maybe in drawing it is not looking as same, but they are same, the same column, same influence zone. Now if I take I am taking for the square grid one column and its influence zone. Similarly you can take the rectangular that triangular grid also. So I am taking that square grid. Now this grid, now what we will do, we will convert this influence zone also an equivalent circle. Okay, we will convert it an equivalent circle. So finally this cell will be, if I convert it to an equivalent circle, so finally it will be column and a equivalent circle. Okay. Now how I will determine the diameter of this circle? How I will determine the diameter of the circle? So you can see that this is the diameter of this circle DE. E means the equivalent diameter, and this is say DC, diameter of the column. Okay, so that means this is the diameter of the column and this is the diameter of the equivalent circle. So this is called that unit cell. So that means we are basically taking one particular column and its surrounding area, and then we are analyzing that. So this is called unit cell. Now here you can say how I will do that, calculate the diameter of this equivalent circle. So I am doing it for the square grid. Similarly it can be done for the rectangular grid, triangular grid and hexagonal grid also. Hexagonal grid I have not shown here, but I am talking about the square grid and the triangular grid. So that means how we will do that? So that means here a square is been converted to an equivalent circle. So the square, so that means if I say this is D, diameter of the equivalent circle, so I can write that pi DE square divided by 4, that is the area, that will be equal to the S square. What is S? S is the spacing between the columns. S is the spacing between the columns. So that means this one is also S. So that means the area of this square grid or the influence zone, that is S square, because if the spacing, S is the spacing. So S is the spacing and D is the diameter. DC is the diameter of the column and D is the diameter of the equivalent circle or influence zone. So now we can write this is D, this area is equal to that square area, so it is A square. So that means we can write that DE will be 2S divided by root pi. So that will be 1.13S. So that means for the square grid, you can see that equivalent diameter of this equivalent area is 1.13S. That is for square grid. Okay, this is for square grid or square pattern. Similarly, DE will be equal to 1.05S, that is for triangular grid. Okay. So, in a triangular grid, how we will do that? This hexagonal area you convert it to equivalent circle. Now, the area of this hexagon will be equal to the area of the circle. So, based on that you can calculate the for triangular grid it is 1.05 S, and for square grid it is 1.13 S. So, from here if you analyze this as a unit cell approach, you can see that this equivalent diameter is 13 times more than the spacing between the columns in case of square grid, and in case of triangular grid it is around 5% more. Okay, so it is 13% more, 1.13. So there is always an overlap between these grids or these unit cells. You can see there is always been overlap between this unit cell. So that sometimes we can consider this small overlap also during your analysis, but this is okay because this overlap is not that huge, and for triangular it is very small, only 5% overlap. For square grid it is around 13% overlap. So, but we use this technique, okay, confidently, and then obviously, if you do the analysis, and you will see that the use of triangular grids is more preferable compared to the square grid, because its performance of the column, I am talking about this performance at a effectiveness as a drainage path, is better in case of triangular grid as compared to square grid, but these both grids are used in the field. So now these are very common. In addition to that, I have this, as mentioned, that there is a hexagonal grid also, where the influence area will be a triangle. So now here a few terms that I want to mention. That one is the stress concentration ratio. What is that? That is the stress on column is divided by stress on soil. And obviously always it is greater than 1, this ratio. Why? Because stone column is a stiffer material compared to the surrounding soil, and if you apply a stress over this unit cell, say over this unit cell or in this whole grid, then obviously the stiffer material will take more stress compared to the weaker material. That is obvious. So that's why as the stone column is a stiffer material, it will take more stress, okay, as compared to the weaker material. So that's why there is a stress difference on the column and on the soil. Suppose if you provide a UDL over this entire zone, so obviously the column will take more load or stress compared to the surrounding soil. So that's why that's called stress concentration ratio, which is stress on column, which is always greater than the stress on the surrounding soil. It will be greater than 1. So that's why this term is generally used for this, representing this stress on column and the soil. Another is the area replacement ratio, which is area of the column divided by total area. So area is the area, AC is the area of the stone column, and A is the total area. So total area means the area of this influence zone, that means pi d square. So it is basically pi d square divided by pi d square by 4 divided by pi dc square by 4, or pi dc square by 4 divided by pi d square by 4. Okay. So these terms are very common terms we use for our design. So, and then now we will discuss about the design methodology. The first, Seed and Booker 1977 developed the mathematical formulation and design charts to design the stone column as liquefaction mitigation, considering infinite permeability of the stone of the column. So this is the reference. You can see that the Seed and Booker stabilization of potentially liquefiable sand deposit using gravel drains or stone column. It is published in Journal of Geotechnical Engineering Division AC, volume 103, number 7, page 757 to 768. So what he is saying that here, so if I obviously if I draw the vertical cross section of the column. Okay, so suppose this is column. Okay, so that means this is DC, diameter of the column, that is been written here as 2RD, radius of the drain, because in the different papers the different notations are being used and the design charts are developed according to that. So that's why it is very difficult to use one particular notation, because when I use the design charts, they have used the different notation. So, but I will try to give you the what are the meaning of those notation, because sometimes they are same meaning, so that I will discuss. But here the RD is the radius of the drain. Okay, it is not saying column, it is radius of the drain, and DC is the diameter of the column. Okay, so that means that DC is both are same, so that's why DC will be equal to 2RD. Okay, so and then there is a influence zone. So suppose if I draw a vertical cross section I am drawing, so there will be influence zone. So this influence zone soil is going radially to the column. This is another thing, that when if you see that, so that means here this influence zone, these influence zone soil water is radially going to this column. Okay. Similarly, this influence zone water is going to this column. So that means here it is radially, this water is entering into the column. So that means suppose if in the consolidation also you have a say 10 meter depth clay layer, and the if you don't use this technique, then the consolidation will be, or the water will flow only the vertical direction, and it has to travel that huge length if I consider the one-way drainage. But if you provide the column, so basically your spacing is say how much, 1.5 meter to 3.5 meter maximum in the if I consider the 3 meters, say that means that part is been reduced, the travel path is been reduced. Now this 3 meter if you provide, the travel path will be even half of that, 1.5 meter roughly. So that means that there it has to travel around say 10 meter or sometimes less, but it is 10 meter, now it is come down to 1.5 meter, and it will travel radially. So that means your travel path of this water is been reduced, which is true for the consolidation and the liquefaction also. This travel path is been reduced. So that means the pore pressure will be dissipated in a faster rate. That is one reason. That means the travel path is been reduced because of this lateral drainage. Another is that that your permeability in the horizontal direction is more than the permeability in the vertical direction. So, that is also another reason. So, that is why that if I provide this technique, then the travel path will be reduced, and due to the higher permeability, your dissipation of the pore water pressure that will generate will be done in a faster rate. Clear? So, that is true for the liquefaction and that is true for the consolidation also, because both are the same technique. It is the function of drainage. So, now, so because of this radial drainage, it will consider the radial drainage, and so now when we talk about the radial drainage, but there will be a radial travel of the water, but at the radial direction, and at the same that there will be a vertical direction also. Now, the overall if you consider a consolidation, say, so overall total degree of consolidation, it can be written 1 minus uv into 1 minus ur. uv is the due to the vertical movement of the water, the degree of consolidation, and another is the due to the lateral movement, and you will say, and I have already discussed that in the lateral direction travel path is small and the permeability is faster. So, the movement of water or the consolidation that you will achieve by radial drainage is much faster than the consolidation that you will achieve by vertical drainage. Okay. So, that is why sometimes in most of the analysis only the radial consolidation or the drainage is being considered, not the vertical. But if you want, you can consider the vertical also, but it has been observed, although depending upon the soil type, that if for a total degree of consolidation, your radial degree of consolidation around 80 to 85% as in a total degree of consolidation, and the remaining will be the vertical consolidation. So, that is why sometimes we neglect the vertical consolidation and we consider the radial consolidation only when you use the stone column. Similarly, in your liquefaction mitigation part also, sometimes we use only the radial drainage, not the vertical drainage, because the radial drainage is much faster than the vertical drainage. Clear? So, so that means here if I consider only the radial drainage here, say, then this will be your RE. This will be RE, that is the radius of the influence zone, because if I draw that plan, so this is my stone column, which is here written as true RD, diameter of the drain, and this one is your RE, that means the radius of the influence zone. D is the drain, E is the influence zone. Okay, so here we can see that if I compare the previous notation, we can write that DE is equal to 2RE and DC will be equal to 2RD. Okay. Now, it is been this Seed and Booker has observed that the UG or del U say, okay, and divided by sigma V dash. So, what is that? It is basically the RU value. You know, So this is basically the RU value. Because I mentioned it is the pore water pressure ratio or the pore pressure ratio. What is RU? RU is the pore pressure ratio. RU is the pore pressure ratio, which is del U by sigma V dash, where is the del U is the excess pore water pressure developed due to n number of cyclic shear stress, n number of cycle actually shear stress application or n number of your uniform stress cycle, that is so that means is del U is the excess pore water pressure development due to n number of cyclic shear stress application or n number of stress cycle, okay, and sigma V bar is the initial, you can put sigma V0, initial consolidation pressure. Stress, okay. So now this RU is a function of, as the Seed and Booker has mentioned, this is function of, what are the parameters? This is function of RD by RE, it is function of NS divided by NL, or I should say this is function of N equivalent and TAD. So one by one I will discuss what is that. So it is function of RD by RE, obviously, because this RD is function of S, because RD is basically the DE. So if you say, you know that my D is equal to, for square grid, 1.13 S, S is the spacing. So DE here your RE RE will be 1.13 divided by 2S, okay. So this will be around 0.564 S. Or if you take it is roughly 0.564, because this 1.13 is also rounded up. So it is, if you directly calculate, it will be around 0.56. So 0.561 or 0.56. So this is 0.56. So that means RE is function of S, and obviously if your S increases, then the travel path will increase. So the time to dissipate the excess pore water pressure, that will also increase. So that means your this RU value, which is the del U by sigma V dash, that should be the function of S. So that is function of RE, and as well as it is function of the drain diameter, because as you more larger diameter, then your effectiveness will be more. Okay. So that means it is been non-dimensional. By generally when you represent this spacing and the diameter, we represent it in terms of non-dimensional form, and that is your spacing by diameter, or reverse will be the diameter by spacing. So here it is represented by diameter of the column or radius of the column divided by diameter or radius of the equivalent circle or influence zone, which is actually the function of spacing. So basically the first part is spacing to diameter ratio or diameter to spacing ratio. So that means your generation of excess pore pressure, that is function of this diameter and the spacing, which is obvious because it depends on the spacing and it depends on the diameter also. So that is one. Second one is N equivalent. What is the second term? N equivalent. What is N equivalent? N equivalent is the number of uniform stress circle. Okay. So here then this one I should remove. This should be the stress cycle only. It is obviously uniform, but this is for any number of the excess pore pressure developed during to n number of stress cycle or application. Okay, so that is also uniform. You can write uniform. It's not an issue. So equivalent the number of uniform stress cycle. Okay, equivalent number of uniform stress cycle, and NL is the number of stress cycle needed or required for initial liquefaction. So that means what is this N equivalent? Equivalent is the number of uniform stress cycle. Okay, that means it is the stress cycle applied on the soil, and NL is the number of stress cycle needed to cause initial liquefaction. Needed for initial. So initial liquefaction, what is initial liquefaction? You know that if this value is 1, then you call it the initial liquefaction, or 1 or 100%. So that means here you can see that liquefaction the same thing, that one is the stress developed during earthquake, another is the stress required to cause an earthquake, and here N equivalent is the number of cycle applied during an earthquake, and NL is the number of cycle required to cause an liquefaction. So if your NL will be equal to N or N equivalent, so that means your applied uniform stress cycle is equal to the stress cycle required to cause an liquefaction. If they are same, so that means there will be just the initiation of the liquefaction. But here definitely we will design it such that we can apply more N equivalent, more stress cycle. That's why we are providing stone column. No? That means it can go 2 times of the number of stress cycle required to cause the liquefaction. So that means your N equivalent will be more than the NL. Then the system will be effective. Because that means we are designing the system such a way that we can apply more number of stress cycle which is required to cause the initial liquefaction. Okay. So for example, if you design it for earthquake magnitude say 7.5, then your N equivalent will be 15, equivalent number of uniform stress cycle. So that is the case. So that means we will design, for example, your initial liquefaction may occur at 7 or 8 cycle, for example. So that means here, in such case, we can provide this system so that our cycle required to cause the liquefaction is say 7 or 8, but I can apply 15 cycle, still there will be no liquefaction. So that is the way we can design it. So and definitely this deluge generation of excess pore pressure, that should be the number of uniform stress cycle or the number of equivalent stress cycle, because as your number of applied cycle will increase, then the this possibility of liquefaction will be more, that will also increase. And another NL is also dependent in such that this for a particular soil, this N number may vary, because that this is the number required to cause the liquefaction. So that means it is the function of these two ratio also. And the third one is the TAD. What is TAD? This TAD basically is equal to KH by gamma W TD divided by MVS into RD square. Okay, so that means here TD is the duration of the earthquake. That means obviously del U should be function of duration of the earthquake. Okay, so in my next lecture I will discuss that because this is a function of these three things, three terms. This first term is the spacing and radius, spacing to radius or radius to spacing. Second term is the number of cycles required to cause the liquefaction and the number of cycle applied or developed during an earthquake. And third term is the duration of the earthquake. So that is also important. So if your duration is more, possibility of liquefaction is also more. So in the next class, I will discuss how using these terms we can design a stone column improved ground considering all these effects. Okay, thank you.